Hey, good morning, gang. I'm going to do a little lesson on just kind of summarizing what I think I consider the big three diffie-Qs. And I'm going to do this and build a Word document that will kind of give us some notes. So bear with me as I'm a little bit clumsy with the equation editor and also the Inspire calculator. We're going to use that a little bit. So let's just grab here. Call this the big three diffie-Qs. Now the first of the big three is the exponential differential equation. So I'll just put this in bold. And the statement of the exponential differential equation is that the rate of change, growth, is proportional to the population. So in other words, the change in the quantity, the instantaneous rate of change of the quantity is proportional to the quantity. We'll say of a population. So, if we do, if we put that in an equation, it's going to look like this. Equals some constant times the population. All right, and we can solve this by separation of variables pretty easily, and we did this in class. And the solution, we'll say the particular solution So our particular solution is P of t equals P naught and then times e to the RT. And that's what you guys know as PERT, right? That's exponential growth, exponential decay. If we'll say if r is greater than 0, we get exponential growth. If r is less than 0, we get exponential decay. Okay, and another equation that's kind of related to this in finance. We have the equation, what's called the present value, future value equation. Sometimes they'll call it present value, sometimes they'll call it future value. And we'll do, just put, this is what the equation is. It's PV, FE, future value, equals the present value of your money, and then times one plus the interest rate divided by the compounding frequency, and then this is all to the, gotta raise that to a power. That's all to the NT. All right, and this is just to specify what this means. FE is future value of your investment. PV is the present value of your investment. R is your interest rate. So like let's say 6% would be 0.06. Okay. N, compounding frequency. That's how many times per year you get paid your interest or your return on your investment. So like N equals 4 would be quarterly. I mean, you get paid your interest 4 times per year. N equals 12 would be monthly. N equals 365 would be daily. And T, that's time in years that the money is invested. Okay, and one of the kind of cool things about this equation is if you take the limit of this equation, so let's say we'll take a limit as the compounding frequency approaches infinity. That means you get paid imagine if you got paid your return on your investment, your interest. Imagine if that got paid every nanosecond. That means that your compounding frequency wouldn't be 4 or 12 or 365, it would be infinity. If you take the limit of this, and I'll copy this down here, this is going to equal, it basically equals this. So basically it ends up being the same exact equation if you take the limit. The limit problem is kind of interesting. It requires a little bit of L'Hopital. We're not going to take the time to do it right now. And this is called exponential compounding, or continuous compounding, because your compounding is going on continuously. Now we can go graph a few of these. Let's grab the Inspire, and let's say we're going to have we'll start with an investment. Let's say insert a graph, and we're going to change to DiffEQ mode, and we'll use P here as our variable. We'll say that P prime equals, and let's say that our investment grows at like 10%, so that would be 0.1 times P. Now we really only care about the first quadrant here, so we can see our slope field here. You can see our axis kind of goes up to $12 here. If I start with, and this is time here in years, so I'm going from 1 year to 17 years. If I want to put in some initial conditions here, I can go up and I'll click here, and actually let's change the slope field resolution here. We can click on this, and we'll scroll down here. We'll go to 42 just to triple that. That'll give us 42 hash marks across the screen. That gives us a little better sense of what's going on with our slope field. And so you can see if we start with investing, let's say at time 0, our x-axis here is really our t-axis. At time 0, if we start with $1, or at time 0 we could start with $3, or at time 0 we could start with, let's say, $6 or something like that. Yeah, and you can see the different solution paths that we're going to get. That's basically all exponential growth. And to give you a sense of what those returns, rates of return would be for investments, the long-term averages for the stock market are around 9 or 10% per year. For bonds are around 3 or 4% per year. For what's called money market instruments, which is real short-term bonds, if you will, the rate of return might be 1 or 2% per year. You know, the more risk you take, the more return you're going to get. So now the stock market hasn't been doing too good. As a matter of fact, the loss over the last month is the biggest ever in the stock market. The stock market is down about 30% just in the last month. So if we were to change this number, the growth rate from 1% to negative 0.1%, I'm sorry, negative 10% is what I meant to say. From 10% to negative 10%. You can see what goes on here is that now basically this would be like the stock market going down, but the value of people's investments is decaying. If you know, you can think of positive rate of growth as, you know, inflationary environment, and a negative rate of growth as a deflationary environment where the prices of things are going down. So this is exponential decay. When it was positive, it was exponential growth. I'll do Control Z just to get back to where we were before. And the other thing is, if I start with $0 here, and you can see, well, if I invest $0, I'm going to get $0 forever, and that's this solution path down here. Okay, the next equation we're going to work on is one that's called Newton's law of cooling. And the statement here is similar to exponential growth and decay, but it's a little bit different. I'm going to say the rate of change of a population is proportional to, we're going to say, the difference between the population and a fixed a constant population value. Okay, and just to give you the equation is very, very similar, but rather than being proportional to the population, you're proportional to some constant minus the population. All right, and in Newton's law of cooling, what we're going to do is we're going to think of that constant as sort of room temperature. All right, so here in Newton's law of cooling, we're going to consider that P of T is the current temperature of an item, or an object. We'll call it a beverage. And K is ambient temperature. I'm just going to call it room temperature. Okay. So you can see that you know, basically in this case, the rate of change, if the room temperature is larger than the temperature of my beverage, so if K is bigger than P, I'm going to get a positive rate of change, and basically my temperature of my beverage is going to be rising. If the temperature of my beverage is higher, it's hotter than room temperature, then I'm going to get a negative rate of change, and that my beverage is going to cool, and that's kind of where this comes from, Newton's law of cooling. Sometimes this, we'll say there's some other ways, forms in which Newton's law of cooling might be written. Sometimes you'll see it written like this. See if I can fix this. Sometimes it'll be written like this. They'll have the P and the K switched up. They'll have a negative sign. Like that. So sometimes you'll see it written like that. Sometimes you'll also see it written like this. They'll kind of divide the right-hand side through. Sometimes they will divide the right-hand side through by K. So it might look a little something like this. They'll say this will be and then this will be a 1 right here. So you can see in this case, if P is greater than K, this term's going to be negative. I'm going to get cooling. If P is less than K, this term's going to be positive, and I'm going to get warming of my beverage. Let me. Oh, we forgot to paste our pictures in here. Well, I'll do that a little bit later. Our graphs when I save this document for you guys. So let's make a couple other notes up here. We're going to say okay. Let's go into an Inspire, and we'll insert a new problem. And we'll try this equation. And insert graph, menu, graph entry, edit, DiffEQ, call this P. Let's try the same rate of growth. I'm not sure how this is going to work out. Let's try 0.1, and let's make our room temperature 70 degrees. We'll say minus P. And you can see our scale isn't really great here. We only are going up to 12 degrees. I want to get up to like maybe 160 degrees here. And let's do, you can see this is, let's call this 17 minutes here. So this is maybe as our coffee is warming or cooling here. Let's change our field resolution. .42. Okay, and now you can kind of see what's going on here, but it's still. Well, let's put some initial conditions in and see what happens. So, whoop, I'm on the wrong equation. So if I put some initial conditions in, I could have my hot coffee from Dunkin' Donuts, and at time 0 it's 150 degrees. I could have my cold Gatorade from Krauser's, and that's 35 degrees. I could also have some lukewarm water that's already 70 degrees, and we could look at that. And so you can see what our solution paths look like. If my in the case of my coffee, it's going to be the case that the temperature of my coffee is going to drop down from 160 degrees, and it's going to approach 70. And the farther away it is from 70, the temperature is from 70, the faster it's going to approach 70. And as it gets close to 70, it slows down. In the same way, for our cold Gatorade, the further it is away from 70, the faster it's going to climb there, but it will slow down. And then this is sort of our equilibrium case. If I bring lukewarm water in here, that's just going to stay 70 degrees. It's perfectly stable. So if I have, the moral of the story here is that if I have I basically have two solution paths here. I really have three different solution paths. I have this one solution, which is kind of a degenerate solution. It's a real simple one. If we went and did separate integrate, we'd end up separate integrate and did separation of variables, did our 6 steps, we would find that we would get a real simple, easy solution to the equation. And if we did separation of variables for any initial condition other than 70, other than the initial temperature being 70, at the branch step, we would have to make a decision. We'd have an absolute value expression there, and that, depending upon whether whether 70 minus p were positive or negative, we would get a different type of solution. So that branch step in separation of variables is the step that really creates these two different families of solutions. If my initial temperature is greater than 70, I'm going to get a solution that looks like this, and it's going to end up having a certain mathematical form that will end up being concave up. Again, if I start with an initial temperature below 70, I'm going to get an entirely different mathematical form that will give me particular solutions that are concave down. So let's put that in our notes, and we'll say for initial conditions, we'll say if p of 0 equals k, we get a solution of p of t equals k. That's our lukewarm water. If p of 0 is greater than k, we get a solution where p prime of t is greater than 0. We get a concave up solution, and that would be hot coffee. And let's just change that one for an initial condition where the initial temperature is less than k. We get a solution that is concave down. So that would be like cold Gatorade. And one of the things you notice about each one of these solutions is that as time approaches infinity, it's the case that the particular solution approaches our room temperature here, that constant K. So we'll put that in as a note. In all three cases, whoops, we'll say in all three cases, the limit as t approaches infinity of p of t is going to equal k. So that's an important thing to know, and just kind of a piece of trivia about that one. Okay, and the third differential equation, which is sort of like what would happen if exponential growth and Newton's law of cooling got together and had a baby. That's called the logistic growth model. And in the logistic growth model, the statement is basically that the rate of change of the rate of change, instantaneous rate of change, is proportional to two things. So it's jointly proportional. We're going to say the population is jointly proportional to the population, and the difference between the population and a constant population value. This is also known as the carrying capacity. So in Newton's law of cooling, K basically meant room temperature. In this case, it means carrying capacity, which is sort of like the natural limit of a population that might be determined by how much food is around, or how many resources are around, and so on and so forth. So let's copy this stuff here, and we'll start to say some things. So the difference here is that it's proportional to the difference from this carrying capacity, but it's also proportional to the population itself. And here P of t is a population. And here K is called the carrying capacity. And some other forms that you might find this one, you might find it to be like this. You might find it to be like this. So you see it in a couple of different forms. Now what we'll do is we'll go into the Inspire and we'll take a whack at doing this and see what the solutions look like. So let's grab the Inspire. We're going to insert a new problem. Graph. I'm going to change to DiffEQ. And what we'll do, we'll start with an example. Let's talk about deer on the hilltop. And what we'll do is we'll say, I'm going to start with a slightly lower value for R here, and we'll see how this works out. We'll say 0.05 or something like that, times P times, and we'll say that that the hilltop, there's enough vegetation on the hilltop to support 200 deer. So 200 is going to be our carrying capacity. And what we're going to do is we're going to run some experiments on how many deer there are over time on the hilltop. So now I got to get my scale right. Let me go down here into this quadrant, and I'm going to need to change my vertical axis significantly. And let me go up to, like, let's say 400 deer. Okay. And all right, so I have, like, it looks like I have 400 deer here. Let me go to negative 20 here. Whoops, I didn't want to do that. I wanted to go to, let's see here. That's about 370. Let me actually just go to Window, Menu, Window Zoom, Window Settings, and I'm going to go. Let's say my X min. We'll say that's -1. That's fine. We'll go to 15 years. We'll make my scale 1. My Y min, I'll make like -20 to just give us a little headroom, and then my Y scale. I'm going to make that 50, and let's see how that turns out. All right, that looks pretty good. Let's get a more granular slope field. We'll change our field resolution here. Let's make that 42. And now what we'll do, it looks like my growth rate is still a little too fast, so let's change this to 0.01. That looks a little bit better. Let's go a little bit smaller even than that. 0.5. That looks a little bit better. All right. So we've chosen our R to be 0.005. Our carrying capacity is 200. And now what we're going to do is we're going to drop some deer on the hilltop. And we're going to do a couple scenarios. Our first initial condition will drop 0 deer on the hilltop. The next one will drop 50 deer on the hilltop. 50. Next one will drop, let's say 150 deer on the hilltop. And then we'll do, let's drop, let's say 300 deer on the hilltop. And you can see the types of solutions that we get. If we start with 0 deer, obviously we're not going to have any reproduction and we get 0 deer. In the case of 50 deer, you can see our solution starts as concave up, but then it switches to concave down right around here, right around 100 deer. It looks like we have an inflection point here. In the case of 150 deer, it's going to be, we're going to have a concave down solution. And in the case of 300 deer, we have a concave up solution. And you can see in all of these cases here, as long as I start with a positive number of deer, eventually I'm going to have 200 deer. And that's basically, what the logistic model is explaining. And right now that's in the news because, what we're trying to do by social distancing is we're trying to reduce this value of K. If you look at the graph the Johns Hopkins graph, the cases in China and what's going on right now. You can see that you can see the I think today, which is March 19th, is the first day that China did not report any new cases. And if we go here and down in the lower right, you can see this graph here of cases in mainland China is a logistic graph. It kind of has an inflection point right here, just just around February 13th, and that's where things kind of started to turn around, and the effect of their social distancing and lockdown helped them out. So so what we're going to do is we'll take some notes on this, and for various initial conditions, we're going to say okay. If well, let's actually go back to here, and we'll change this initial condition down here. Let's say we started with exactly 200 deer. And you can see now we get a straight line solution. In the case of 50 deer, this is great. The deer are thriving, they're reproducing, it's a big party. Same thing here at 150 deer, but at 150 we're a little closer to the end of the party. Whereas in the case of 300 deer, it's the starving time, right? We have starvation and a depletion of the population. So in the case where our initial condition is the carrying capacity, we get a straight line solution. So that's basically constant population. If we get, if we have a case where our initial population is greater than the carrying capacity, then we still get a concave up solution. If we have an initial condition where the population is less than the carrying capacity, but also greater than, we'll say half the carrying capacity, then we get a solution that is concave down. And now, why is that? Why is that the breaking point? We'll explain in a second. And then we have this scenario too, where if our initial population, like in the case of 50 deer, if we have this kind of scenario, where the initial population is somewhere between 0 and half the carrying capacity, we get a solution with an inflection point. At P of T equals half the carrying capacity. Okay, and there's a reason why that is. If we wanted to find the inflection point, what we would do is we take the second derivative and set it equal to 0. So if we took the derivative of the first derivative, we'll say, let's take the derivative of, take the derivative with respect to t of dp dt. That's going to be the derivative with respect to t of this, right? Which is going to be the derivative with respect to t of RKP minus RP squared. And that's a simple quadratic. The derivative is going to be RK minus 2RP. And if we set that equal to 0, and we can solve for P. So let's do that. So you can see that this special place in the logistic model where basically half the carrying capacity, that is a special spot. And it's a special spot for a couple reasons. One is that it's an inflection point of the solution in this case. We'll say that K over 2 is an inflection point of the particular solution. And we could also say that that's also the point where the growth rate of the population is at a relative and absolute maximum. All right. So if we go back to our inspire here, and we look at, you can see the steepest, that here this the solution path is steep, and then it gets its steepest right here, and then it starts to get less steep. So it makes sense that the relative maximum of the first derivative would occur at an inflection point of the original function. All right. So that's a summary. I'll paste these graphs in here and post these along with the notes.